Welcome, ladies and gentlemen. I'm Rosemary Bartlett with the Pacific Northwest National Laboratory, and I'd like to welcome you to today's webcast, Residential Requirements of the 2009 International Energy Conservation Code, brought to you by the U.S. Department of Energy's Building Energy Codes Program. We're very happy to have as our speaker today Todd Taylor of the Pacific Northwest National Laboratory. Todd, please begin.
Thank you, Rose, and welcome everyone. As Rose mentioned, we are talking about the residential portions of the 2009 International Energy Conservation Code, IECC, today, and we will jump right into it. To begin with, let's briefly kind of overview what this code is. This is one of a fairly large family of codes that the International Code Council puts out. We call them the I-codes. The additional codes that are out there include all your plumbing codes, your building codes, mechanical, etc. And of course, our interest today is the energy conservation portion, the 2009 in particular. There is one other code. You'll notice the blue picture at the top right there, the International Residential Code, also has some energy provisions in it. Chapter 11 contains those energy provisions, and they are in many ways very similar to the IECC's requirements, but there are some differences, and so I'll talk briefly about the relationship between the two. The IECC addresses energy efficiency only, whereas the IRC is a full standalone code for all matters related to residential buildings, where residential is restricted to 1- and 2-family dwellings and townhouses that are 3 stories or fewer. The IECC addresses both residential and commercial, and would include some residential buildings that are not included under the IRC, in particular apartments and that sort of thing that are not covered in the 1- and 2-family dwelling code, you might call it. The energy efficiency requirements in these two documents are almost identical. There are a few differences in stringency. I've listed the 2 primary ones here. The IRC only has a 0.35 solar heat gain coefficient requirements in the southern 3 zones, whereas the IECC requires a bit more stringent 0.3. And there are a few foundation requirements that are less stringent in the northern zones in the IRC. And there are some other differences that are relatively minor in terms of energy consumption, but that's all we'll talk about there. We are focusing today on the IECC, and in particular we're focusing on Chapter 4 of the IECC, which relates to residential energy efficiency. If you are familiar with the prior versions of the IECC, in particular with the 2006, I'll cover briefly a few of the things that have changed since then, but we won't focus on those for most of this presentation. We will assume that you have no knowledge of the codes at all, so you won't need any past history here. In the 2009 edition, some of the envelope requirements got a bit more stringent. I won't go into what those are. More importantly, there were several new requirements added, and these really, the early ones of these I'll mention, are some of the more significant changes that have ever made it into the IECC in terms of saving energy. There is a requirement new in 2009 for pressure testing of ducts in buildings. Unless the ducts are completely inside conditioned space, there's a requirement that they be pressure tested to make sure that the sealing requirements have been met. There are some similar new requirements related to envelope air sealing. You can either test the whole house with a blower door, do a pressure test, or there's a fairly extensive checklist that must be inspected bit by bit by the code official. And the builder can choose either way to go there. There are, for the first time, restrictions on lighting in the 2009 IECC. There are some limits on the efficacy of the lamps that go into permanently installed fixtures. There are a few new requirements for pools and snow melt systems that we'll talk about briefly as we go. Some of the moisture control requirements that used to be in the IECC, in particular the requirements related to vapor retarders in the building envelope, have been moved over, and the IECC now relies on provisions in the IRC, and those have been modified there to permit more flexibility in the way vapor retarders are implemented. A big change in the 09 version of the code is that you are no longer permitted to trade HVAC efficiency against reduced envelope efficiency. That's a very new thing. It has some far-reaching impacts in terms of how compliance is checked and just in terms of what the buildings are going to look like when they comply with this code. The performance path has some other changes as well that we won't go into today. For the most part, those would be buried in the software tools that you use to comply anyway. To begin with, let's take an overview of the structure of this code and to make sure we have a clear view of what's coming, and then we'll get into the details. We'll be covering things like the the front matter of the code itself, what the climate zones are, the scope, what's covered, the general nature of the requirements, and so forth. With regard to climate zones, the climate zones in the IECC, as you see drawn here on the figure, are defined entirely by county boundaries. You can see each and every county in the U.S. is drawn on this map. And once you know the county in which the building is being built, you know which requirements apply out of the code. This is different from many codes of the past where you had to know the local heating degree days or cooling degree days or both. You no longer are required to know those climate parameters for any location within the continental or within the United States. And what that means is the requirements within every county are homogeneous. They're the same. You don't have any two buildings that are subject to different requirements within a county. As you can see the numbered zones on the map here, there are 8 temperature-oriented zones. The bottom tip of Florida you see is climate zone 1, and as the numbers go up, you move generally north over on the east side of the United States. That general south to north variation kind of breaks down in the mountain states, but still the 8 climate zones relate to temperature. Those are crossed with 3 moisture regimes. As you see across the top of the slide here, the moist regime, also known as A, is for the most part the eastern half of the United States. The dry regime is the mountain states and the desert southwest. And the marine is the strip along the Pacific coast that has that marine environment. So those 8 zones and 3 regimes give you a theoretical total of 24 possible zones. However, within the United States, only 15 of those combinations actually occur. And when it gets to the residential requirements, which we're focusing on, for the most part, the moisture regimes are not used in the residential portion. So it turns out that there are really only 7 unique zones as far as the residential portions of the code are concerned. One other thing to notice, you'll see a white line snaking through the middle of Zone 3 in the southeastern part of the U.S. That white line defines what's known as the warm, humid counties. And those counties are based on ASHRAE's definition of a warm, humid climate. They are different from the moisture regimes. For the most part, they are not used in the code yet. The thing is there primarily to accommodate things like economizers in the commercial side of the code where humidity considerations are important. The only place that line is used in the residential code is with regard to basement requirements in Zone 3, where the warm, humid portions of Zone 3 do not have any requirement for basement insulation. The scope of the IECC. We've already mentioned we're referring today to residential buildings, and I think I've already said the IRC energy chapter covers only 1- and 2-family dwellings and townhouses, whereas the IECC covers all low-rise residential, all occupancies except those that would relate to, for example, hotels and motels. So if you're going to apply a multifamily apartment building, for example, you must use the IECC rather than the residential IRC Chapter 11. Any building that is not residential, according to the definitions above, is defined as commercial in the code and would comply under Chapter 5, which we won't talk about today. The scope of the code does include repairs, alterations, and additions. We'll talk more about those in a moment. There are certain buildings that are exempted from the requirements of this code. Very low energy use buildings, those with that are designed to use overall less than 1 watt per square foot, for example, are exempted. Buildings or even portions of buildings that are not conditioned are exempt from this code. Existing buildings are exempt, meaning that if you purchase an existing home, you're not required to bring it up to the specs of this code simply because it changed hands. And finally, there are some allowances for historic buildings so that you don't have to modify the historical aesthetic aspects of the building to match this code. With regard to additions and alterations, renovations, this code applies to any new construction that goes in on the home, but it is not required that you bring the rest of the home up to the requirements of the code when you alter another portion of it. If you put an addition on a new home or on an existing home, you have your choice of either making sure that that additional room or whatever it is added to the home complies with this code on its own, or you can demonstrate that the entire building, including the new portion, complies when it's all said and done. And that would typically involve the energy performance analysis path, which we'll talk about a bit later. And finally, any unconditioned space in the home that is converted to be conditioned has to be brought into full compliance with this code. There are a few exceptions to additions and renovations with regard to applying the code to them. Applying storm windows, for example, over existing fenestration does not trigger a requirement that the glazing be brought up to the specs of this code. If you replace only the glass within a window, leaving the sash and frame in place, you're not required to bring the windows up to code. Basically, if you open up a building cavity and that cavity is already filled with insulation, you're not required to bring that up to the level of the current code. For example, if you open a wall that's 2x4 wall with R13 in it in a climate zone where the 2009 code would require R20, as long as that cavity is already filled with insulation, you're not required to bring it up to R20. You can leave it at R13, even if you opened it during the renovation. And other requirements or other allowances, anything that you don't open, even though you're working near it, does not have to be brought up to code. Finally, mixed-use buildings. There are a few of those out there, fairly straightforward in terms of scope. The portion of that building that has a residential occupancy is required to be compliant with the residential portions of this code, and the other portions of the building that would be considered commercial occupancy will have to comply with Chapter 5. An overview of the general structure of the IECC. Most of the requirements that people are familiar with are climate specific. In other words, for things like insulation and walls and windows, ceilings, foundations, and so forth, those vary with climate. There are some other requirements in the code that are universal. They apply everywhere regardless of climate. Typically those are related to HVAC systems and so forth. But also infiltration control systems, for example, are universal. The IECC has some terminology in it that we need to get cleared up because it's not used in this manner in most of the rest of the I codes. When the IECC refers to a requirement that is prescriptive, that basically means it's a required element of the code, but you can trade it down or even trade it away by increasing the efficiency of another building component. So, for example, if the code requires R20 walls, you can trade that down and put in an R13 wall if you improve some other portion of the building, the ceilings or the windows, in a manner that compensates for that change in efficiency. When the code refers to a requirement that's mandatory, that's a requirement that cannot be traded down or away under any circumstances, even in the full performance simulation path. So those terms will be used several times as we go through this presentation, and you need to remember what they mean. There are a few elements in this code that have what are often referred to as hard limits, also known as trade-off limits. And these are basically prescriptive requirements. In other words, they're requirements that you can trade down, but they can only be traded so far. And we'll talk about those in detail when we come to them. The major categories that are covered in this code, the building envelope, that is the focus. That's where we'll spend most of our time today. That's what most people think of when they think of the requirements of an energy code. There are some limited requirements on HVAC and systems, and I say limited because the federal law preemptively regulates equipment efficiency itself. So it's only the systems and related machinery that this code impacts. Lighting, as I mentioned earlier, is a brand new requirement in 2009. The requirement is fairly simple. We'll talk about it more later, but basically 50% of the lamps in permanent fixtures must be high efficacy. And a high efficacy lamp would be something like a compact fluorescent bulb. And note that this is based on a simple count of the bulbs, not the fixtures or the watts or anything like that. It's a count of bulbs. So one fixture with a large number of lamps in it can have a big influence on the fraction of lighting that's high or not high efficacy. There are a few other systems outside the home itself that are covered by this code: pools, snow melt systems, and so forth. And I note appliances simply to make the point that there are no requirements for any appliances beyond the ones that have been mentioned in here. The one thing that you might think of is water heating, and that's included under the HVAC and systems category. Compliance paths. If you're reading the IECC for the first time, you might have a hard time figuring out what the compliance paths are. They're not straightforward in the code itself. So I'll talk first, very literally, what the code says, and then I'll give you a slide here in a second that gives the more practical understanding of what those compliance paths are. As I mentioned earlier, there are some requirements that are labeled as mandatory. Those must be met regardless of which compliance path you take. And then you have a choice in the code, either a performance approach where you do an energy calculation to show your compliance, or a prescriptive approach. And then under the language in the IECC, the prescriptive approach has three alternatives. You can either choose to do an R-value computation, which is a misnomer, by the way, because there are no computations required when you do an R-value compliance, or a U-factor alternative, or a total UA alternative. All three of those, as far as the text of the code is concerned, are prescriptive approaches. It's important to note that if you use the R-value computation, there are no trade-offs at all permitted. You take what's in the table. The U-factor alternative is very similar to the R-value prescriptive computation. No trade-offs allowed. It simply bases the component requirements on their U-factors rather than R-values. So it's essentially equivalent. The total UA alternative uses the same U-factor tables as the previous one, but it does allow you to make trade-offs across building elements. In other words, you can trade better walls for worse ceilings or something like that, as long as the building element involved is characterized by a U-factor rather than, for example, a solar heat gain coefficient or anything else. The performance path, the full performance path, allows all trade-offs. although as I noted earlier, as of the 2009 IECC, it is not permitted to trade down any envelope measures in trade for better HVAC efficiency. So that's the literal way the code interprets its own compliance stats. In a more practical sense, there are either 2 or 3 approaches to compliance, depending on how you look at it. There's the prescriptive R-value approach over on the left, looking at it in terms of 3 paths. Then there's a UA path in the middle where you can do simple trade-offs based on UAs, and then a simulated performance path on the far right that involves software. And note that the prescriptive, what I've called prescriptive, the R-value one, uses one table. The other 2 paths use the U-factor table. So you're working from one of 2 tables via one of 3 practical paths. And once you get your head around that, it's not so complicated. We keep talking about the R-value path, and in fact, this is probably the best-known table in the entire code. So I'll show it to you here in overview. Notice along the left-hand side that there are 7 unique climate zones. As I mentioned earlier, the moisture regimes are largely absent from the definition of the residential climate zones. The one exception being that the climate zone 4 marine portions are lumped in with climate zone 5 for residential purposes here, and zones 7 and 8 are combined into one zone. So there are 7 rows in the table. Each column then is a component of the building, and for the most part, those components are labeled in terms of R value. We'll talk about those in detail. You'll also notice there are a lot of footnotes at the bottom of this table, a lot of further restrictions, allowances, exemptions, and so forth that are explained down there. We will talk about many of those as we go through this. It's worthy to note that there are more than R values in the R value table. Some of the columns actually have U factors in them. Some of them have solar heat gain coefficients. But predominantly, the insulation requirements in this table are expressed in terms of R value, and that's why it's typically referred to as the R value table. The U factor and total UA alternatives, the U factor alternative itself is very similar to the prescriptive R value table, but it uses U factors to characterize those components rather than R values. This simply allows you to make use of less common construction techniques such as structural insulated panels, or perhaps advanced framing, whereby you get a better R value for a better U factor out of a lower R value, and so the code would allow you to do that. But the U factor alternative itself allows no trade-offs between building components. The total UA alternative uses the same U factor table, but it does allow trade-offs across U factor-based components, and this is the primary alternative. For example, if you're familiar with the ResCheck software, that's used in that software. Here's a picture of the U factor table, very, very similar to the R value table, the only difference being it's expressed in terms of U factors rather than R values. With regard to compliance tools, what kind of a tool is required to demonstrate compliance? With regard to prescriptive, and by that I mean the R value approach, there's really no tool needed. The table says R30, you put in R30 and you're done. The total UA alternative can be done with hand calculations, although very few people will want to do that. Typically you're going to use some software such as the Department of Energy's ResCheck software, or something else that's put out by a private company. On the energy performance path, the energy analysis that's requires the code itself requires that software be used, and it has some minimal requirements of that software. You're going to be using something like DO2 or Energy Plus or one of the proprietary type tools such as rim design, energy gauge, and there are others. So those are the tools that would be involved for these various compliance paths. Let's jump into the details of the requirements. We will start by talking about the building envelope itself and the prescriptive requirements related to that. And we will tend to focus on the R-value table to describe what the code requires as we go through this, but always bear in mind that you could also comply via a U-factor for the component we're talking about, or you could trade that component against improvements elsewhere if you wanted to lower the R-value. Start with ceilings. You can see the column here in the R-value table. Fairly straightforward requirements for R30 in zones 1 through 3, 38 in 4 and 5, and 49 in the northern zones. It's not quite as simple as it appears there, because there are many helpful exemptions and allowances regarding ceilings to make it easy to comply without having to depart from the simple R-value table. With regard to ceilings underneath attics, the R-value table assumes that you're using a standard truss system. That standard truss system tends to put the top cord of the truss, the rafter, if you will, right down to the top plate of the wall, so that you have a restriction in that corner where you can't get the full thickness of the insulation. And when the code, for example, requires an R38, it is assuming that you won't have a full R38 out there near the eaves because it's constricted. There are several problems with that. You get those cold corners where they're not very well insulated that can contribute to condensation up there in the attic, which brings with it mold growth and rot and other problems. It can also contribute to the possibility of ice dam formation, as heat from the house melts snow on the roof right there at the corner. That melted snow runs down onto the eave where it refreezes and builds up a dam that can push water back underneath the shingles. So because of those issues, the R-value prescriptive path encourages the use of raised heel trusses, whereby the top cord does not come right down to the top of the wall plate, but is raised up a bit so that you can get the full thickness of insulation all the way out to the wall. That eliminates those cold spots and the problems that go with it. And if you use that kind of an energy truss, as it's called sometimes, you're permitted to lower the R-value requirements in some of the zones. Anywhere where the prescriptive requirement is R38, you're permitted to use R30 if you have a raised heel truss that gives you full thickness all the way out over the wall. And similarly, if the R-value table has a requirement of R49, you can comply with R38 if you have a full truss out there. Do be aware that this allowance applies only to the R-value prescriptive path, not the U-factor table. The U-factor table accounts for that automatically, because the U-factor will account for the lack of insulation in those corners of the attic. Ceilings without attics, this would be your typical vaulted ceiling or cathedral ceiling. There are some helpful allowances here, again, to make it easy to comply with the R-value table without having to go to the U-factor or UA alternative. And basically, if the vaulted ceiling has a requirement from the table that exceeds R30, but the rafters or trusses that are involved there are not large enough to accommodate that higher R value, then you can comply with not more than R30 for up to 500 square feet or 20% of the total insulated ceiling area, whichever is less. So for example, if you have a small vaulted ceiling over the entryway, and because it's small, it has relatively small framing members up above, and you're in a northern climate where R38 is required, the code will allow you to put R30 in instead. In other words, it will not require you to redesign the structure of the building, putting in larger framing members just to accommodate the R38, as long as the area, again, is less than 500 square feet or 20% of the ceiling area. Finally, there are some requirements related to access hatches into the attic. This actually applies to access hatches and doors between any conditioned and unconditioned spaces, but for the most part, this is doors and hatches into the attic or perhaps into a crawl space. There's a requirement to insulate those doors, and in particular, you have to insulate it to the same level as the surrounding element that it's in. So if you have an access hatch into an attic with R38, the access hatch itself has to be insulated to R38 with with appropriate provisions to, for example, a baffle or a wall retainer to hold loose fill insulation away from that opening when it's opened. There's also a requirement that you give access to any equipment that's up there without the repair person having to step on the insulation. You can't just blow insulation all around the air handler. You must build a platform up to the air handler that's over the insulation, for example. Moving on to above-grade walls. Above-grade walls includes both standard walls between the conditioned space and the outdoors, walls such as knee walls that have perhaps an attic space on the other side or perhaps a crawl space on the other side. And it also includes the areas around the rim joists, which likewise have to be insulated to the same level as the walls themselves. Looking at the column, you'll notice it's labeled wood frame wall R value. There are some special requirements and allowances for different types of walls, whether they be concrete masonry, log walls, steel frame, and we'll talk about those as we go. Notice that R13 is a requirement through Zone 4. Zones 5 and 6 have an R20 or 13 plus 5. Now, it's important to understand with regard to the wall requirements, any combination of insulation within the wall cavity or in terms of a sheathing insulation on the outside, which we would call continuous. It's not broken up by framing members. Will meet the requirement. So the R13 requirement could be met with an R10 in the wall cavity plus an R3 sheathing on the outside, or R13 completely in the cavity, or if you wanted to, R13 sheathing with no cavity. Any combination will work. There is one exception. In Zones 4 and 5, the R20 requirement can be met by a combination of R13 cavity insulation plus an R5 insulating sheathing. To talk about some of the special cases, what the table calls a mass wall, that would be concrete block, solid log walls, anything with sufficient mass that it's able to store a significant amount of heat within the wall itself. There are special requirements for those that acknowledge the fact that that storage ability of the wall can improve the performance of that wall in terms of energy, especially in southern locations for cooling purposes. Now the two numbers you see in that column, the 3/4 in Zone 1, the second number, the higher number, applies when more than half of the R value is going to be on the inside of the wall mass. And what that means is the thermally massive walls lose a lot of their advantage when you insulate the building from them. So it's much better from an energy standpoint to have the insulation on the outside of a thermally massive wall than it is to have it on the inside. So if you have most of the insulation on the inside, you have to have a little bit more of it. With regard to steel frame walls, there's a separate table. There's no column in the R value table related to it. You'll notice there are several categories in this table for ceilings and walls and floors. But the important point to understand this table is it's all based on the wood frame R value requirement from the previous table, from the R value table. So the very top example in there for a steel truss ceiling, if the zone you're in has a requirement of R30 for a wood frame ceiling, then for a steel truss ceiling, you would be required to use R38 or R30 in the cavity plus at least an R3 continuous that covers the framing members, or R26 plus 5 that covers the framing members, and so forth. So it's based on finding an equivalent system that will perform equivalently to the wood frame requirement that's in the R value table. As I mentioned, when it says R26 plus 5, that means the first number can be cavity, and it means you must have at least the second number, R5, that covers the framing itself and is continuous along the ceiling or wall or whatever. There is an exception in the southern climate zones. You can reduce that second number, that continuous number, down to R3, regardless of what it is in the table, if you're using walls that are on 24-inch centers, meaning you have less of the wall area taken up by the steel framing. And in ceilings, insulation that exceeds the height of the framing is required to cover the framing. You can't just put a bat stacked up high with gaps in between it over the framing members. You must cover the framing members if the thickness would allow it. Fenestration. There are 3 columns in this table related to fenestration. They are not R value requirements. They're U factors and solar heat gain coefficients. And it's important to understand what the columns mean. In general, in the IECC, the definition of fenestration includes all windows, all glazing, all doors, whether opaque or not. But with regard to this table, skylights, for example, which would normally be considered part of the fenestration in the building, have a separate requirement. So you would use the skylight column rather than the fenestration column for any skylight requirements. And similarly, the third column that says glazed fenestration, which relates to the solar heat gain coefficient, that includes all glazed fenestration, both skylights and vertical, and any glazing within doors, but of course it would not apply to opaque doors. The solar heat gain coefficient requirements are limited to climate zones 1 through 3, which is the southern portions of the U.S. It's important to note that both the fenestration U factor and solar heat gain requirements, and this would be true of all fenestration, including skylights, the requirements themselves are based on area-weighted averages. What that means is if the requirement, for example, is 0.5, you could either have all your windows to be 0.5, or you could have half of them 0.6, half of them 0.4, and they would average out to 0.5, and that would comply as well. It's all based on an area-weighted average as defined in the equation there. Multiply each Window's U factor by its particular area, sum up all those products, divide by the total glazing area, and you get the area-weighted average U factor, which is what's being regulated in the code. There is a requirement that products be rated by NFRC, the National Fenestration Rating Council, and certified according to their rules. There are some exceptions. Just based on the nature of the default U factors for unrated products, any single pane product will comply in Zone 1, and any double pane product that has a thermally improved frame, like aluminum with a thermal break, will comply in Zone 2. They're similar to some of the requirement or some of the allowances in ceilings in the R value table. There are some exemptions with regard to fenestration to make it easy to comply through the R value table without having to go to one of the more complicated compliance paths. There is an exemption of up to 15 square feet of glazing per dwelling unit, completely at the builder's option. This would, for example, allow you to have a decorative side light around the front door, or a glazing unit, some sort of a decorative thing that you bought at a art show to use as a small window in the hallway. Anything like that that's not going to have a rated value. If it's less than 15 square feet, you can just ignore it, pretend that it's not there, and not worry about it in the code compliance process. There's also an exemption, if needed, of one side-hinged opaque door assembly up to 24 square feet. Again, to accommodate some sort of a decorative door or unusual door, you can just leave that out of compliance altogether. One final comment: any replacement fenestration that includes both glazing and sash must be brought up to code. I mentioned earlier that if you replace only the glass, you're not required to bring it up to code, but if you replace glass and the sash, you must. Trade-off limits. Fenestration, both U-factor and solar heat gain coefficient, are subject to trade-off limits. They are prescriptive requirements, which means typically they can be traded off against other building elements, but there are limits to how far you can trade them. And the table here shows the absolute maximum U-factor allowed in climate zones 4 and 5 is 0.48. Zones 6 through 8 is 0.4. Now the prescriptive requirement for those zones is 0.35. If you wanted to have it higher than 0.35, you're going to have to beef up another part of the building regardless. But regardless of how much you improve the walls and the ceiling and the floor, you cannot have a U-factor that's worse than 0.48 in zones 4 and 5. The hard limit for skylights is 0.75 in zones 4 through 8. Once again, the trade-off limits are based on area-weighted averages of all the glazing in the building, all the fenestration in the building, I should say. So you can have individual glazing units that exceed this U-factor maximum of 0.48 as long as the average in the building does not. Solar heat gain coefficient, very similar. Zones 1 through 3 typically are prescriptively have a 0.3 requirement, a maximum allowable solar heat gain coefficient of 0.3. You can trade that up to a 0.5 through the performance path, but not beyond 0.5. And again, that's an area-weighted average as well. Moving on to floors over unconditioned space. It's labeled in the R-value table simply as floor. The numbers are fairly straightforward in here. There's typically not a continuous R-value listed for a floor R-value. But you would simply sum any cavity plus continuous to get this number if you did have such a thing. There is one exception to accommodate floor framing through the R-value table. If the framing members are too small to accommodate R30, for example, insulation that fills the framing cavity is deemed to comply as long as it is not less than R19. So in those two zones, that would be that's off the edge of the slide here, but zones 4 and 5, I guess, that have an R30 requirement. If your floor framing members are not large enough to accommodate that, you are permitted to use R19 as long as that fills the cavity. Floors over unconditioned space, note that the definition of unconditioned space would include outdoor air, it would include an unconditioned crawl space, an unheated basement, a garage underneath, anything like that that is not directly conditioned. One final requirement, the insulation in the floor framing members, if it does not completely fill the cavity, the gap cannot be against the underside of the subfloor. The insulation must be pushed up to be in substantial contact with the subfloor and held up by one means or another. That's to prevent airflow up above the insulation, which could short circuit its insulating ability. Moving on to foundations, in particular below-grade walls as they're defined in the code. Typically they're called basement walls, and in fact that's how they're labeled in the table here itself. Once again, the column has more than one number. When there is a requirement, there are two numbers. The 5/13, the 5 refers to the requirement if it's continuous insulation, which would typically be a foam board of some sort that's usually mounted on the outside of the foundation wall against the dirt. The 13 would refer to cavity insulation if you had furred in and finished the inside of the basement wall and put insulation between framing members. You're not required to have both of those. That's an either or. There are some specific allowances. The R15 cavity or 15 continuous or 19 cavity requirement can be met by a combination of 13 cavity plus 5 continuous on the outside. And if I mentioned earlier that the only place in the code where the warm, humid county definition comes into play is with regard to the Zone 3 basement wall requirements, which is an R5 continuous or R13 cavity. That is not required in the counties defined as warm, humid according to ASHRAE's definition. Note that the definition of a below-grade wall in the IECC is any wall that is more than 50% below grade. We'll talk more about that here in a second. If the wall itself is more than halfway above grade, it's going to be required to meet the R value requirements for an above grade wall. The insulation depth, it must go down all the way to the basement floor or 10 feet below grade, whichever is less. Now talking about that definition of 50% below grade, here's a quick illustration of a typical walkout basement. The back wall in that basement, which is clearly completely below grade, is obviously a basement wall and would be subject to the basement wall requirements. The front wall, which is clearly all above grade, would have to meet the requirements for an above grade exterior wall frame, or if it's a masonry wall, the mask wall column. The two side walls are a little bit ambiguous. It depends on what fraction of those walls is above grade or below grade as to whether the entire wall is categorized as a basement wall or an above grade wall. So it's probably to your advantage to be sure that the plans themselves specify where the backfill is going to go and how much of that wall is going to be buried. Because if you assume that most of it will be buried and build it with the basement wall R value requirements, but the dirt contractor doesn't backfill all the way and 3/4 of the wall ends up being above grade, you may not end up complying with the energy code because you wouldn't be meeting the appropriate wall requirements. Slab edge insulation. It's defined in the R value table with two numbers again. The first one being the R value of the insulation required, the second being the depth to which it must extend. The southern zones, typically 1 through 3, have no requirement for R value at all. The next two zones only need 2-foot depth, but an R10. The northern zones an R4. Important to understand, and this is in a footnote in the table, there's an additional R5 required if you have a heated slab. So where the requirement is now R0, it would become R5. Where it's now R10, it would become R15 in a heated slab. The definition of a slab edge application is to a floor surface that's not more than 12 inches below grade. If you've got your slab any deeper than that, you're dealing with a shallow basement, and those other requirements would come into play. When the code says 2-foot depth or 4-foot depth, that can be any combination of vertical or horizontal extension of the insulation. And you can see here 3 examples of insulating down, let's just, that looks like maybe 2-foot depth. It's 2-foot depth either inside the stem wall or outside, or it can extend inward under the slab. And what's not shown here, it could also extend outward under the dirt as long as there's at least 10 inches of soil over it for protection. If you look at that middle figure, you'll notice the insulation itself is between the slab and the stem wall, which for some people makes it problematic, difficult to attach flooring and such on the inside of the home. So there is an allowance in that case to cut the insulation at a 45-degree angle so that the concrete of the slab extends closer to the stem wall. There's also an allowance in the code for any location where the code official deems the termite infestation to be very heavy. You are completely exempted from the requirement of slab edge insulation. Crawlspace wall insulation. This is different from insulation over the crawl space, but if you have a conditioned crawl space, as some people call it, there are separate requirements. Once again, 2 numbers. The first one refers to continuous insulation, like a board or a blanket. The second refers to insulation between framing members on a furred-in basis of some sort. Obviously, this implies that the crawl space itself is unvented, or as some people would say, conditioned. There are requirements that the space not have the potential for moisture buildup. The 2 things that govern that are, 1, making sure that there is a minimal amount of airflow through that space, and that can be done either with mechanical exhaust or a minimal bit of supply air. And finally, the exposed earth underneath must be covered with a Class 1 vapor retarder, such as the plastic that you're familiar with. Just to compare what's going on between a vented and an unvented crawl space, the typical vented crawl space is going to have insulation in the floor over the crawl space, whereas an unvented crawl space will have insulation on the crawl space walls. The vented crawl space is probably or possibly required to have a vapor retarder as part of the floor assembly, whereas the unvented space is going to be required to have a vapor retarder on the ground surface underneath. The vented crawl space has requirements for ventilation openings around the crawl space wall, whereas the unvented crawl space must be mechanically vented one way or another, either with pure exhaust or actually by bringing some conditioned air in. Ducts in the crawl space, because they're in unconditioned space in a vented crawl space, must be insulated to R6, whereas if you insulate it on the stem wall and you have or on the crawl space wall and you have an unvented space, that is conditioned space, and you don't have to insulate any ducts that are down there. Moving on to HVAC and systems. This covers a number of areas in here. We'll talk about equipment efficiency and some of the related systems and controls. Most of these are what we would call mandatory requirements. Looking at the list here, nearly everything involved is mandatory, which means there are no trade-offs permitted. The only thing you see on this page that is prescriptive is the insulation on the ducts. It's the only thing that through the performance path you can trade down that R6 requirement to, I believe, as low as R4 if you make compensating improvements elsewhere. HVAC equipment, which is perhaps one of the most important systems-related energy features, is really not dealt with directly in the IECC because federal law establishes minimum efficiencies via a DOE rulemaking, and those federal requirements preempt any state or local building codes. And so the IECC generally just points to the federal minimums as what's required in the home. The multifamily applications, if you have systems that serve multiple dwelling units rather than a separate system for each dwelling unit, you're not subject to the residential chapter of the IECC. You must comply through the relevant chapters of the commercial chapter relevant sections, I should say, of the commercial chapter, 503 and 504. Ducts, as we've mentioned, must be insulated if they're in unconditioned space. Supply ducts in attics must be insulated to R8. All other ducts, both supply and return, must be insulated to R6. It is mandatory that the ducts be sealed in accordance with the IRC joint and seam specifications. You're not permitted to use building framing cavities, for example, as supply ducts, and there is a required test of the air tightness to verify that the sealing has been done correctly. This duct tightness test is a new thing in the 2009. It's fairly complicated because to look at anyway in the code because it tries to be very flexible, but it's really pretty straightforward. The tightness test is required, and you have two major approaches you can take as a builder. Choose either one. You can test post-construction when the building has been completed, all the drywall is in and everything is sealed up, or you can test immediately after rough-in of the HVAC system with the ductwork, your choice. If you test post-construction, there are specific limits on either leakage to outdoors or total leakage, some of which might be to the indoors. You can choose either one of those to comply with, and there are specifications for how the test is done. If you choose the rough-in test, you can only test total leakage. There's no leakage to outdoors alternative. And the requirements of that test are more stringent because not all of the duct system will be in place. The registers are not sealed against the ceiling drywall and so forth. The one exception to this tightness test is that if the ducts and air handler are completely inside conditioned space, you don't have to test the tightness. You do still have to seal the ducts, but there's no requirement for a test. There are requirements for a programmable thermostat on any forced air system with specific requirements regarding what temperatures it can maintain, and even there are requirements for how the thing must be initially programmed. Set point temperature no higher than 70 for heating, for example, no lower than 78 for cooling, and so forth. Moving on, there is a requirement on heat pumps that the supplementary heat, the electric resistance backup, must be capable of being locked out when it's not needed, except during defrost and so forth. Most of these things are controls that are pretty standard in most buildings, but they are required by the code. Any piping related to the HVAC system for a hydronic distribution system, for example, is required to be insulated to R3. The only exceptions being pipes that carry fluids that are not very cold or not very hot. Domestic water heating piping, in contrast, if it's a circulating system, is required to be insulated to R2 rather than R3. There are some requirements for ventilation in the building as well as equipment sizing. The ventilation requirements simply say that any outdoor intakes or exhausts have to have a gravity or an automatic damper that will close it when the ventilation system is not operating. However, there is not any requirement for whether those intakes and exhausts be present or how many of them, simply what they have to look like if they are there. The code does require that equipment be sized properly. It makes reference to section 1401.3 of the IRC and requires use of something like the ACA Manual J to do the calculations. And there are limits. The intent is to get the HVAC system sized correctly so that it operates as efficiently as possible. Moving on to the rest of the code, the other requirements, I'm calling them here. A lot of things, some of these more important in the energy picture than others. We'll talk about them roughly in order here, and they are roughly more important at the top of the list. With regard to envelope air leakage, there are many, many places where the air can leak in and out of the building. Recessed lighting is one big one. If you have recessed lighting that goes up between the conditioned space and into an attic space, There are some specific requirements related to those. Fireplaces or other areas where a lot of leakage can happen if they're not done correctly. But in general, the code does require that all penetrations through the building be caulked or sealed or gasketed in one way or the other. All joints and seams similarly covered and wrapped and so forth. To be sure that the builder has done a thorough job of sealing all those holes, there are two options for the code official. There's the builder can either choose to perform a whole house pressure test with a blower door system to make sure that the leakage of the envelope is not more than what's expected, or there's a fairly thorough checklist in the code that can be field verified by the code official as an alternative. Many places in the building that must be dealt with and sealed correctly, and in the opinion of many, simply doing the blower door test is the cleaner way to discover whether everything has been done correctly rather than inspecting everything. But the code does require either alternative. Lighting equipment, brand new one in the code. There is a requirement that at least 50% of the lamps in permanently fixtured lighting fixtures or permanently installed lighting fixtures be high efficacy. And there is a definition of what high efficacy means, as you see down at the bottom of this slide. Basically, your compact fluorescent bulbs will meet that requirement. Your incandescent ones will not, and there are certainly other technologies out there and on the horizon that will likewise meet these high efficacy requirements, but that's the common example. Note, the 50% limit is on account of lamps, not fixtures. And that can be confusing to some, but you're counting lamps. If there's 2 lamps in the fixture, you count 2. Recessed lighting fixtures are required to be rated for insulation contact when they are up in insulation. There's a requirement that they be sealed with a gasket where they touch for example, the drywall and the ceiling or whatever covering is there to limit infiltration through that opening. With regard to additions, we talked a little bit about this earlier. It's very easy in the 2009 code to treat them as a standalone building or a portion of the building. In other words, to ignore the rest of the building and simply make the new space comply. The prescriptive requirements are designed such that that's easy to do because there are no considerations of glazing percentages and so forth, which tend to get or can tend to be very large when you're looking at a single room. The code has some relaxed, if you will, requirements for some of the exterior surfaces of sunrooms, provided certain things are true. Now, the definition of a sunroom is a single-story structure with glazing area exceeding 40% of that one-room structure or one-story structure's gross wall plus roof area. It must have a separate heating or cooling system or be zoned as a separate zone. And it must be thermally isolated. In other words, it's going to need to have closable doors or windows between it and the rest of the house. If those things are true, then there are a few relaxed requirements for various parts of that sunroom. I won't go into detail there. There are some requirements for snow melt systems. If you have a snow melt system on the driveway, there's a requirement for an automatic shutoff when the pavement temperature exceeds 50 degrees Fahrenheit and there's no precipitation falling. And there's also a requirement for a manual shutoff when the outdoor temperature itself exceeds 40 degrees. There's requirements for pool heaters. They must have accessible on-off switches, and you cannot have a pilot light, a continuously burning pilot light on any gas-fired pool heater. Requirements for time switches to deal with those heaters and pumps, as long as other health standards don't apply, or you're not using solar systems to heat the pool. And then there's a requirement for a pool cover to be left with the pool at the time of construction. If the pool is going to be heated to anything in excess of 90 degrees Fahrenheit, there must be a vapor retardant pool cover. Limiting the evaporation of water is very important in terms of avoiding energy loss. You're accepted from that as long as the pool is heated at least 60% by a solar or site-recovered energy source. Fireplaces must have gasketed doors and must take their combustion air from outdoors. Okay, we're winding down near the end. We'll back up now and look what's placed generally toward the beginning of the code book in the first few chapters, the compliance options, the administrative requirements. We've alluded to the simulated performance alternative a little bit. We won't talk about it much here today, but it does require software. You're basically having to model with the software two buildings, one building that exactly meets the prescriptive requirements, and a second building that's designed according to your proposed home, as long as your proposed house uses less energy or energy cost, depending on your jurisdiction, than the prescriptive home, you comply. Section 405 of the code sets up the ground rules for how you do those energy comparisons. Most of those ground rules will be hidden in the software tool that you use. It's not at all unsimilar to the kinds of rules that you may be familiar with through home energy rating systems, federal tax credits, Energy Star homes, and so forth. So that's all we'll say with regard to the simulated performance alternative. Usually you have a bit of software that's going to take care of most of that, most of those details for you. There is a requirement in the code that you leave with the home a certificate that explains the major energy features of the home. It has to be posted, permanently posted in or on the electrical distribution panel where the occupant, ultimate occupant can find it. Of course, you can't cover any of the required labels related to the panel itself, but it must be there to explain to the homeowner what's in the building. The major major building elements, what their R values and U factors are, must be on there. The solar heat gain coefficient of the fenestration, HVAC efficiencies, and so forth must be listed there. If there's one odd example, to say it's odd, it may strike you as odd. There's one requirement that if you have, for example, a baseboard electric heater, you're not permitted to say that that's a 100% efficient system. You have to simply explain what it is, a baseboard electric heater. And the reason for that is it can be confusing to see a home with a very nice condensing furnace that only has a 91% efficiency, and the building next door that has an expensive to operate electric heater has 100% showing. That can be confusing to an occupant who doesn't understand the difference. So there are specific requirements for labeling the type of equipment when it's an electric system, for example. Various compliance and documentation and inspection boilerplate. Most of you, if you have worked with building codes at all, will be familiar with most of this. The local official, as always, is the final authority in all matters. The code makes explicit allowance for electronic media to be used to turn in the documentation for code compliance, and so forth. The code official is permitted to demand a permit for any work that's going to be done and to conduct an inspection when that's done. And we just mentioned, of course, the certificate that's required. Mostly boilerplate here. I won't go into detail on it, but I believe we have covered the entire 2009 code.
Well, thanks, Todd, and thanks to all of you. The U.S. Department of Energy appreciates your attendance today.